Hello all, we are continuing our discussion on integer programming solution methods. We started learning the branch and bound algorithm in our previous video tutorial. In this one we will continue our discussion. I will first give you the formal branch and bound algorithm, the steps of the algorithm in a formal way. Then we will make more examples on solving branch and bound algorithm using branch and bound algorithm to solve integer programs with general integer variables. After that, in the following video tutorial, we will learn how to solve problems, integer programming formulations with binary decision variables using the branch and bound algorithm. So let's continue with the algorithm. In the previous tutorial, I already gave you this general scheme of the branch and bound algorithm. So this is not the formal algorithm. I will give you the formal algorithm in the next step. But this is the informal way of providing the steps of the algorithm. Okay. So what are these steps? The first step is to relax. Okay. When you have an integer linear program, we relax any integer variable. We replace them as their continuous variables. If the variable is binary, then we replace it in this way. If it is general integer, we basically replace it with, for example, y greater than or equal to 0. This is the first step. The second step is to solve the LP relaxation. Since it is LP, we can use the simplex algorithm to solve it, and we find an optimum solution. And depending on the solution value, in the third step, we make a decision either to fathom or cut that branch or to continue with that branch. And this decision depends on the solution of the LP relaxation. LP relaxation gives us information about the infeasibility, about the optimality, and about the bound of the integer program. And depending on that, if we decide to continue with that branch, then we will add some spatial constraints and we will continue with that. Let's continue with the formal algorithm. So the steps of the algorithm in a more formal way is given here. But when you are reading such algorithms, in the first read, you may not understand some steps. Don't be stressed, okay? Just read it to the end of the algorithm and then return back and read it again and read it again, because in such algorithms there are loops. So what happens, you continue until step 3, and in step 3 it says that go back to step 1. So step 1 is written in such a way that if the algorithm follows through step 3 or comes from step 0, it can repeat the tasks in that step. That's why please don't be stressed. Just read the algorithm till to the end and then reread it and you will understand it. Okay, the branch and bound algorithm for a maximization problem and for a minimization problem have small differences. Basically, these differences is a result of having whether you got a lower bound or an upper bound from the LP relaxation or from the integer feasible solution. That's why you have to be careful. First, I'm going to give you the steps of the branch and bound algorithm for a maximization problem. Later on, I will show which parts of this algorithm should be changed in a minimization problem. Step 0 in algorithms, there's always a step 0. Step 0 is in fact the initialization step. Okay, so here you initialize your counters and etc. in the algorithms. For example, in this branch and bound algorithm, it says that set z equals to minus infinity. Z here represents the objective function value of the integer solution. Okay, so whenever I say z, you should understand that it's the objective function value. And what we do initially, we set it to minus infinity. Since we don't know any integer solution yet, we set its value to minus infinity. It's minus infinity because this is a maximization problem. Okay. I will talk later. If it was a minimization problem, then you will start with a plus infinity. Okay. So initially, since we don't have an integer solution, we set its value to minus infinity. And we set this index I, it will be a counter. We set its value equals to 0. Okay, we start from this one. Then step 1 of the algorithm. It says that this step makes fathoming or bounding. Remember the example that we solved in the previous tutorial. We were just fathoming some branch due to several reasons. And in fact, this step does those fathoming operation on the branch. Okay, it says that select LPI. So what is I? I comes from here. Initially, I is 0. Okay, but as we proceed, I will increase LP1, LP2, LP3. In the previous example, we started with LP1. The first relaxation that we solved was represented as LP1, right? But it may change. I mean, in different books, you may see different representations. Some of them say that the first LP that we solve, which is the root node, remember, we have a node here, then depending on the solution, we branch it and add some constraints. So what should be the number in this node? We said that this node can be sometimes referred to as root node, root of the tree. Okay, so some books give 1 to this one and say that this is the LP1 that we are solving. But in some other books, they say that this is LP0. Okay, so it starts with 0. It's not important, but this algorithm is given according to having this node as 0, okay, numbered as 0. So it starts with LP0. Okay, here it says that select LP0. Since I is 0, we start with 0. The next sub problem to be examined. So if we just started, it is the LP that we are going to examine. But if we evaluated some steps and in, for example, step 2 or step 3, we return back to step 1, then this will be LP1 or LP3 or LP5, whatever the I index is. Okay. Select LPI as the next sub problem to be examined and then solve it. How? If you have only 2 variables, you can use the graphical solution method. But usually we use the simplex algorithm to solve it. Okay? And then when you solve it, if you have one of these 3 conditions, then fathom it. Okay? According to these 3 conditions, we will try to fathom it. What are these 3 conditions? Let's look at first one. The optimal z value of LPI, so when you solve this LP, the optimal solution, objective function value of that solution, says that cannot yield a better objective value than the current lower bound. Okay, so we are in a maximization problem and it says that the current lower bound. Since we just started, we set the lower bound, this is lower bound, okay? The current lower bound is minus infinity. But as soon as we find an integer solution, let's assume that we found a solution with objective function value 100, and this is integer feasible solution. This is not the LP solution. This is an integer solution. Okay? Then the lower bound becomes 100. Okay? Then you solve another LP, and when you solve it, the objective function value of that LP for example, becomes 80, less than the integer that you already found. Okay, what does this say that? Okay, in the branch and bound tree, let's assume that you follow this, and we are currently in such a branch. Okay, then we solved this LP, or let's say we solved this LP, and the objective function value of this LP relaxation, LP, is 80. And we already found the solution with 100. We have an integer solution with 100. So it means that if you continue with this node, if you evaluate the nodes under this one, you will not be able to find a solution which has an objective function value greater than 80. Okay? You will not be able to find that solution with an objective function value greater than 80 under these nodes. Why? Because under this node means that you are adding constraints to your model, adding constraints. When you add a constraint, your objective function value cannot improve. It either stays the same or it worsens. Okay, so we are trying to maximize, we solve an LP here to maximize an objective function value, and its value is 80. Then if you branch it and solve a solution here, then you have one more constraint here. And with that one more constraint, your objective function value cannot be more than 80. So this 80 tells you that this L80 tells you that the solution, the best solution that you can obtain from the nodes under this one, from all over the nodes under this one, the maximum value that you will get is 80. But you already have a solution with 100. Then there is no reason to continue here. You already have a better solution for a maximization. 100 is better than 80. So we fathom this node. Okay, this first one is the most, let's say, complex one to understand for new learning students. The others are pretty easy. And this is the reason for fathoming for such a case is called fathom by bound. Okay, so we are fathoming, we are deciding not to continue with this node furthermore because it will not yield a better objective function value than my current best solution. So we fathom this node. Okay, this is the first reason. The second reason, okay, you solve this LP and then that LP yields a better feasible integer solution than the current lower bound. In fact, it doesn't need to be a better feasible integer. You can just delete this one. If LPI yields a better feasible, if LPI yields a feasible integer solution, then we fathom it. But depending on its value, we may do two things. Okay, so those are explained here. What are they? We solve this LP. Remember, it's still an LP. But when we solve it, the decision variables appear to be integers. Although we relax them, the result is integer. Then we say that this is an integer solution for my original problem. Okay. Now, assume we already have this integer solution, 100. And you found a new solution here. If that solution is 80, for a maximization problem, 80 is worse than 100. So what do? We terminate, we fathom this node, and we do nothing. We continue with the other nodes. Still, the best solution that we found is 100. But on the other hand, if instead of 80, after solving this, you find a solution with, let's say, 120 objective function value. This is integer and its value is 120. You already have a solution with 100. You are trying to maximize. So it means that 120 is better than 100. So again, we terminate, we fathom, but we do one more thing. We update the lower bound. Now my new lower bound, the best solution that I found becomes 120. I continue with this one. Okay, so in this step 2, in this part B of step 1, when you solve an LP, if you find an integer solution, you need to check that solution with your previous best solution. If the new solution is better than the older one, you update it. Otherwise, you keep the old one. Okay, if this is the first step, our initial lower bound is minus infinity, right? We started with that one. Then we find the solution, integer solution at this step. So this solution should be better than minus infinity all the time. It means that as soon as you find your first integer solution, you update its value. That minus infinity becomes a new value that you obtain from here. Okay, so this is the second reason of fathoming. And the third reason of fathoming, by the way, for this one we said that it's fathom by bound. For this one, you can say that fathom by integer feasibility or fathom by optimality. But this is optimality of that branch, not the whole problem. So maybe it's better to say that fathom because of feasibility for this case. Okay. So I'm having a little bit difficulty writing here feasibility. Okay, it's understood, I guess. And the last alternative for fathoming is this. Again, we solve this problem in this branch. We solve it. And this is an LP. We try to solve it. But the thing is, there is no solution to this LP. That LP is infeasible. There is no solution that satisfies all the constraints of this LP. It means that that LP is infeasible. Then what should be our decision? Basically, our decision is this. If the LP is infeasible, then the integer problem corresponding to that LP should also be infeasible. And we fathom in this case because of infeasibility. Okay, fathom by infeasibility. In fact, these three cases, if you remember our video tutorial on relaxation and their uses, these three cases are directly related with that part. Basically, we said that with a relaxation, we can prove optimality, okay, which is this one, in fact. We can prove infeasibility, which is this one, the third alternative, okay. And we can calculate upper or lower bounds depending on the optimal objective function value, which is this one. So this A, B, C are connected with the relaxation and their uses. At the end of this step 1, two cases may arise. What are they? If the LPI is fathomed due to these reasons, and then you found a better solution, as I said in step B, then you update the previous lower bound. Okay? Otherwise, you don't update and you continue with the rest of the branch and bound. If all subproblems have been fathomed, when you fathom this new one, if there are no other subproblems in the branch and bound tree, then we stop. You see, this is the stopping criteria, the stopping condition of the algorithm. There shouldn't be any other problems, sub-problems that you haven't solved. When you stop, then what's the optimum solution? The optimum solution is the solution which gives you the lower bound. Okay? Initially we start with minus infinity. Then whenever we find an integer solution in this part, if it is better than the previous one, we update it. And then when we stop the algorithm, the optimum solution will be the lower bound in your hand. Okay? But it says that if no finite lower bound exists, I mean when you stop the algorithm and your lower bound is still minus infinity. In this case, it means that this problem has no integer feasible solution. This problem that you try to solve is infeasible. Okay? Otherwise, if none of these cases, none of these conditions hold, then what do? We increase our index. Remember, we started with index 0, then solve this first LP0 here. Depending on that, we tried to fathom it. But if none of these conditions hold and we cannot fathom it, then we increase the value of, one of these three conditions hold, but none of these conditions hold here. We cannot stop the algorithm. Then what do? We increase the index by 1. So if it is 0, we increase it to 1. If it is 1, we increase it to 2. Then go back and repeat this step 1 again. Okay? What do we mean? We terminated this node due to one of these reasons, but still there are some other sub-problems that are not terminated, so we cannot stop. We continue by selecting another node and repeating the steps on that node. Otherwise, at the end of step 1, what can also happen? We cannot fathom this branch, this node, due to one of these reasons. We cannot fathom it. So it means that we need to continue. We need to continue on branching. So it says that go to step 2 for branching. So in this slide, what we learned, we start with the root node, node 0, and then we move to step 1. We select the next LP to evaluate, we solve it, and depending on the solution, if that solution is worse than my lower bound, then we fathom it. If that solution is integer feasible, we fathom it. If that LP has no feasible solution, we fathom it. If we cannot fathom, we branch it, and we will learn how to branch in step 2. Okay, now let's move to step 2. As I said, don't be stressed. We will continue to the end of this algorithm, and I will summarize all of them once again, and we will solve examples repeating the steps of the algorithm again. Okay, so let's continue. So this step 2 of the algorithm is the branching step. We come to step 2 from step 1. In step 1, we solve an LP, relaxation LP1, LP2 in the branch and bound tree. We solve it. We have the solution. We try to fathom it due to one of these three reasons, but we cannot. Okay? So we come to this step. We couldn't fathom it, and we came to this step. And what does it say? In the LP solution, it says that select one of the integer variables whose optimum value in the LPI solution is not integer. In the original problem, xj is an integer restricted variable. Okay? But when we solve the relaxed problem, this relaxed optimum for this LP is not integer. Okay. So let's assume that we started with root node and we followed these, let's say, and in some node, we are currently here, we solve this LP in this node. And then in the solution, we have a, let's say, decision variable x3. whose value is, let's say, 4.2. Okay, it's not integer, but in the original problem it's restricted to be integer. Then what shall we do? Okay, we need to branch this node, and while branching this node we need to eliminate the region where this x3 is not integer. So how did we do in the previous example? We said that, okay, if it is 4.2, we take the integer value less than this one, which is 4. So we say that x3 less than or equal to 4 on this side. And on the right hand side, we say that x3 is greater than or equal to 5. Both of them are greater than or equal to. So we eliminate the region between x3, between 4 and 5 for x3 by adding these two constraints. So this is branching. And in branching, this is the classical branching. In this classical branching, we always branch into two. Okay? x4, x3 less than or equal to 4, greater than or equal to 5 on the one hand side. By the way, so if we said that on this left hand side, x3 is less than or equal to 4, and on the right hand side we said x3 greater than or equal to 5. But it's not important. You could write here x3 greater than 5 on the left hand side and less than 4 on the right hand side. It will not make a difference in the final solution. Okay? But since 4 is on the left, on the timeline, on the, let's say, number line, and 5 is on the right, it's maybe more convenient, easy to understand, the right, x3 less than or equal to 4 to the left and greater than or equal to 5 to the right. Okay, this step, if you read this step, you may be confused. It says that, okay, eliminate the region where xj is less than, xj star in this parenthesis is less than xj, and etc, etc. Basically, what does it say is this: if you got 4.2, then you should eliminate the region for this x3 where it cannot take any integer values between 4 and 5. So this xj star here in parentheses, or xj star 1 in parentheses, according to my example, is 4 and 5. If this x3 was not 4.2, but if it is, let's say, 3.7, then you should have 3 less than x3 less than 4. Okay, so we want to eliminate this region, and in order to eliminate this region, it says that write these constraints. And what are these constraints? Again, according to my example, x3 is less than or equal to 4. Okay, x3 less than or equal to 4. So this says that add this constraint, and x3 greater than or equal to 5, as I did in this branch and bound. Okay, so basically in this branching step, you get the solution of the LP. So you take one of the decision variables whose value is not an integer. There may be more than one such variables. For example, x3 is 4.2, and also, let's say, x5 can be 7.5. So there are two, let's say, decision variables which are not integers. Which one to select? You can select anyone. Basically, there are some rules. You can use some rules, but it does, no one knows selecting which one is the best. So you can select one of them randomly. Okay, but basically, as a rule of thumb, what you can say, if one of these x3 or x5, if one of them is more closer to an integer value, for example 4.2, it's very close to 4, but when you look x5, it's 7.5. It is not too close to 7 or to 8, but 4.2 is closer to 4. So in that case, you may decide to select x3 instead of x5. Okay? But as I said, you can select anyone, no problem. Okay, we select one of these decision variables and we add these two constraints and we branch that node into two by adding the constraints. And the next line, final line of the algorithm says that set increase the value of I to I plus 1. So we are solving LPIs. Now we will solve LP I plus 1 in the next step and return back to step 1. Step 1 was the previous step. So you will select the next LP and solve it. Try to fathom it. If you cannot fathom it, you will come to this step to branch it. Okay? So let's continue. Okay. So these are the steps. Step 0, initialization. Step 1, trying to fathom. And step 2, branching. And as soon as you do, you return back to step 1. So there's a loop between step 1 and the algorithm stops whenever all branches, all nodes are fathomed. There are no LPs that you are going to solve again. So the algorithm stops at that time. So these steps of the algorithm that I provided to you was for a maximization problem. But the thing is, we can solve a minimization problem with the branch and bound tree as well. In that case, what shall we do? In the next slide, I will talk about it. And also, we can use the branch and bound algorithm for mixed integer problems. Not only pure integer ones, but we can use it with mixed integer ones. Remember, what's a mixed integer problem? There are some decision variables which are integers, but there are some of them which are continuous. Then how can we use the branch and bound tree for such a problem? The main idea is the same, but what you will do, continuous variable, they are LP, they are continuous. We just deal with the integer variables. So we relax the integer variables and we branch on the integer variables. We never branch on continuous variables. Okay? They are already continuous. We don't deal with them. We just ignore them. We continue with the integer variables. We first relax them, solve the problem, and depending on the reasons that I mentioned, we branch only the integer variables. Okay, so let's continue with minimization problems. Now let's consider the branch and bound algorithm for a minimization problem. Basically, the algorithm is exactly the same. Here, I just highlighted the parts of the algorithm that we need to change according to a minimization problem. Remember, initially, for a maximization problem, we set our initial lower bound to minus infinity. This is for maximization. Now, for minimization, we need to make it opposite. So we need to set initial solution to plus infinity. Okay? Then in step 1 of the algorithm, again, what do? We solve the LPI, the next LP. And depending on its solution, we try to fathom it. The first reason of fathoming is if this LPI cannot yield a better objective function value than the current lower bound, it says, current integer solution. So for a minimization problem, current integer solution is not a lower bound, but an upper bound. So this should be changed to upper bound. The second reason is if LPI yields a better feasible integer solution, then the current, again, it's upper bound. Okay? So the third one, LPI has no feasible solution. It's the same. Then it says that two cases will arise according at the end of step 1. First case, if LPI is fathomed and the better solution is found, a better integer solution, then we need to update our upper bound, not the lower bound, in a minimization problem. If all subproblems have been fathomed, then we stop. The optimum integer linear programming solution is associated with the current finite upper bound. If no finite upper bound exists, which means that if your upper bound, when you stop the algorithm, if your upper bound is still equals to plus infinity, then there is no feasible solution to in this integer program. Otherwise, we set I equals to I plus 1 and repeat this step. Or the second case is this. If LPI is not fathomed, we go to the step 2. Okay, so the step 1 of the algorithm, the changes that we need to make for a minimization problem are these. Initially, we set the z value to plus infinity. Then we replace every lower bound in the algorithm with upper bound. When you look at step 2 of the algorithm, which was the branching step, everything is exactly the same for a minimization and for a maximization problem. We solve the LP and we find an integer restricted variable x, which is not integer. Then in order to eliminate this region, we add two constraints, this x less than or equal to the integer less than the value of that variable and greater than one plus that integer value. And then we set I equals to I plus 1 and go to step 1.